Yes, good evening, Anirudh. Okay, it's 6:02. I'll start from 6:05. I'm just waiting for 2-3 minutes extra, another 2-3 minutes. Then I will start. Okay, everything is okay. Just waiting for extra another 1 minute. After that, I will start assignment 7 problem solving session. Okay. If you face any problem, you can ask in message section. Okay. If you face any problem, um, so am I audible and visible? Please respond. Okay. So any if you face any problem, any type of problem, you can write it in a message section. Okay. 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 So it's already 6:05. I waited for 5 minutes. Now we can start our problem solving session. So welcome to problem solving session of week 7. I am going to solve assignment problem 7. So myself, Amiya Mandal, I am a PMR scholar of IIT Roorkee and working under Professor K.L. Yadav, under the supervision of Professor K.L. Yadav. And I am doing here a PMR as a PMRF TA. And the course code you already know about the fundamentals and applications of dielectric ceramics. Today, I am going to solve the assignment problems of 7, week 7. As you already uh, learned much about in week 7 lectures. So what you have learned in week 7, sorry, it should be week 7. Okay. it should be its lenses. Okay. Okay. So what you have learned in week 7, uh, you have learned some basics of ferroelectric materials, um, and some basics of ferroelectric materials, its response in electric field. Okay, how it responds in electric field, how it uh, tran transition phase transition, ferroelectric phase transition. You also have learned about. Okay, first order phase transition, second order phase transition, and how the free energy is varying here. Okay, everything. And how the susceptibility, dielectric constant, polarization varies with temperature at different temperatures. So everything you have learned in week 7, uh, all the problems are based on these concepts, and I will uh, clear every concepts of every problems as I have done in previous lectures also. Similar thing I am going to do this in this lectures also. So, and all extra thing, that is thermodynamics of phase transition you have also learned in these topics, ferroelectrics. And most importantly, second order phase transition first, then first order phase transition of ferroelectric materials. You have learned this, and every problems are based on these topics. So I am going to solve one by one every problems. There are 15 problems total. Okay. So let's see what the question number 1 tells about. Okay, just read the question number 1. Okay. It is telling about ferroelectric material. Sorry. A ferroelectric material has the following attributes. There are 4 options. So in this question, mainly discussing about the ferroelectric material, basics of ferroelectric material. Okay. So, so it has a centrosymmetric crystal structure. It exhibits structural transition across field temperature, or it show a polarization versus electric field hysteresis, or it is the same as an electret. Okay. So first of all, we try to understand what is centrosymmetric and what is non-centrosymmetric. Two types of crystals are there. Uh, so here you already learned in previous weeks, and I already have told many things about centrosymmetric and non-centrosymmetric crystals on week 6 also, and I'm going to tell in week 7 also that centrosymmetric, one is centrosymmetric and another is non-centrosymmetric. Okay. Centrosymmetric means there must be a symmetry in unit crystal, that if 2 points in a crystal, let this crystal lattice are symmetric with this point, this is a center point, and this is x, y, z, then it should be minus x minus y minus z. So these 2 points are symmetric with this point. So which shows the crystal family shows these types of symmetry are called centrosymmetric crystals. Okay. So as you have already know about that 32 crystal point groups. About there are 32 crystal point groups in the crystal lattice. Out of them, 21 are 21 are non-centrosymmetric, means it do not follow central symmetry with respect to this point, with respect to this point. Okay, they are showing non-centrosymmetry, means crystal not having center of symmetry. Okay. And other 11s are centrosymmetric. Okay, other 11s are centrosymmetric, 21 are non-centrosymmetric. This gives 32 crystal, 32 point groups. Okay. And the term centrosymmetry refers to the space group which contains an inverse center as one of its center symmetry element. For every point xyz in the unit cell, there is an indistinguishable point of minus x minus y minus z. What I have told in this. And so this is a table which is showing about some centrosymmetric point groups and non-centrosymmetric point groups with 32 total point groups. This centrosymmetric point groups involves 11 point groups, and this involves 21. Okay. Out of them, one is this do not show in the previous lecture also. So 21 are non-centrosymmetric. There are 7 types of crystal: cubic, tetragonal, orthorhombic, hexagonal crystal classes, trigonal, monoclinic, triclinic. So there are 7 types of crystal structures in 3 dimensions. And according to them, they are centrosymmetric and point group nonpolar. Okay, centrosymmetry and non-centrosymmetry variation has been shown here. Non-centrosymmetric means it should be polar. It may be polar or it may not be polar, means non-polar. Okay, so for polarization, in this case, some polar non-centrosymmetric crystal. This is very important, that polar non-centrosymmetric crystal. Ferroelectricity comes in these classes, that the polarization along the polar axis can be reversed by reversing the polarity of the crystal. This is the most important property of the polarization. Most important property of polarization, that if we reverse the polarity of the electric field, means if we reverse the electric field direction, okay, then polarization direction also goes reverses according to the electric field. This is the behavior for polarization of ferroelectrics. So these are spontaneously polarized material with reversible polarization. Okay. So these types of groups, polar non-centrosymmetric groups, means these are the this shows the polarization, ferroelectric behavior. This is the schematic diagram. You can see that with the application of electric field, the direction that is XY, the polarization is also increasing accordingly and decreasing accordingly after reversing the direction of electric field. Okay, that's hysteresis. We learned known about this, and we also learned about it. So this is the dielectric constant plot. But you can see that there is a certain peak of dielectric constant at a certain temperature. Tc, it's called Curie temperature. Okay, we learn much more about this. Or epsilon, that is dielectric constant. So I have collected it from this source. Okay. So you can see this figure showing about polarization versus electric field group. This is a typical PE or hysteresis of a ferroelectric. Okay, this is a typical PE or hysteresis of a ferroelectric. Stable Okay, just wait for some minute. Let's see. Okay, I was just checking whether it is working or not. Okay, so okay, okay. So this is you have learned this in a lecture series of grade 7 that this is a typical PE loop or hysteresis loop. Okay, stable hysteresis loop where we can, if we increase the electric field from this position, it is increasing in this line, it is increasing in this line, and at a certain point, it is going to stable. Then, after reversing the electric field, this stability at this point, this is the remnant polarization PR. This is the saturation polarization plus PS. And in this region, it is going to be switching process, switching. We'll just learn it later. So this is the electrical analog of ferromagnetic material. In magnetism cases, Ma is called M versus H. If we increase the magnetic field corresponding the magnetic polarization is also generated there. So here a hysteresis. So these do not follow the same path. The electric field is the electric field, the polarization. So there must be a polarization in this material. This is called spontaneous polarization. Okay. So this PR represents remnant polarization, PS represents saturation polarization, EC represents coercive field. Coercive fields is this field in which the polarization is going to be zero. So here some polarization, some remnant polarization are there inside the material. After the application of the field zero, and then still the some polarization exists in the material. It, it it's not zero after the application of electric field, zero. So to make it zero means if we want to take a zero polarization in the material, we have to apply this much amount of electric field. That is negative electric field, that is negative coercive field to get it a zero value. Okay. Okay, there is also one thing that is electret. Okay, the ferroelectric materials are stable, means after the application of electric field, it's going to stable at a certain point. Okay, saturation polarization, we get a saturation polarization, but there is a similar type of material that's called electret. Electret. So what electret do? In case of electret, we do not get a stable value. In the case of what we have got in the case of ferroelectric material, we do not get in the case of a electret material. Okay. So electret materials are somewhat different from ferroelectric material by on the basis of stability, stability of polarization. Okay. So polarization, ferroelectric, so stability value, ferroelectric are stable and it is not stable, electret. Okay. It's not stable. So polarization. So what are the main difference between electrodes and uh, ferroelectric materials? Main difference is polarization. Electrodes have a quasi-permanent electric field on their surface, while ferroelectric material has spontaneous polarization. This is the main difference, mainly. So, in this basis, we can tell that it's a metastable state, and ferroelectric materials are in thermodynamic equilibrium, also thermodynamic equilibrium. Okay. And polarization retention. Electrodes made from low leakage materials can retain polarization for many years, while ferroelectric materials can retain polarization permanently. Okay, uses microphone. Okay, so it is uses in ferroelectric capacitor. So these are the some basic concepts about ferroelectric materials. So on this basis, we can now see that what will be the answer. Ferroelectric material has the following attributes. Number one, it has centrosymmetric crystal structure. No, it has a non-centrosymmetric crystal structure. Then it exhibits a structural transition across Curie temperature. That is correct. It exhibits a structural transition across Curie temperature. Okay, as you have already learned about that, uh, for a dielectric cases, that when you learn about polarization versus Q, I can see that for a second order phase transition, it exhibits surface transition from ferroelectric to paraelectric state. Also, in case of dielectric versus, there is a clear phase transition at a Curie temperature from ferroelectric to paraelectric phase. Okay, this temperature is called the Curie temperature. So, ferroelectric state and paraelectric state, what does it imply? If you see in lead zirconium, lead zirconate or lead titanate, okay. If you see this, you can see that in an unit cell, sorry, there are different titanium atoms, oxygen atoms. At octahedral position, there is a titanium, and at this point, unit cell there consist of lead. Okay, we already have learned about this. Just so this is titanium octahedral. PiO6 minus octahedral. Okay, so if its central position intakes in this direction, then it is termed as a paraelectric material. Okay. So these paraphase and ferrophase transitions are uh, seen in a ferroelectric material also. Next option is it shows a polarization versus electric field hysteresis law on the application of an electric field. This also is correct. Okay. It is the same as an electric? No. So these two options are incorrect. 1 and 3. Okay. Next we are going to the question number 2. Okay. At a temperature T greater than Tc, in the free energy versus polarization plot of a ferroelectric system, which are true? Free energy versus polarization plot, G versus polarization plot at a temperature T, you have learned about this type of figure. Okay. This type of figure. Yeah. So you already have learned about this type of figure where one minima is arising in a paraelectric state. Okay, so when it occurs, so in paraelectric state, E is equal to 0. It indicates paraelectric state. This indicates paraelectric states, not ferroelectric state. For ferroelectric state, E not equal to 0. Okay. So in paraelectric state, so in order to compute non-zero polarization and susceptibility phi at the transition point, the value of the energy P equal to 0 and P equal to P naught must be equal to Tc. Okay. So at P equal to P naught, G naught value indicates this G naught equal to 0. On the other hand, the field must also be 0. So del G del P is equal to 0 for the polarization to be spontaneous. So del G del P must be 0 there. Okay. Let's see what we have learned in lecture, that if A, B, and C, these are the terms which are temperature dependent. A, B, C, everything are dependent function of temperature. Function of temperature. Here, temperature dependent. Okay. In this G, free energy. Free energy is a function of A, B, C. You already have seen that. Now, AP plus so AP BP P to the power 6 equal to 0, but P equal to 0. Okay. G equal to 0 as G equal to 0, ignoring higher terms. So what does this equation indicating? What does this equation indicating? Uh, this equation indicating that if every A, B, C are positive, it means A, B, C are greater than 0, then what does it happen? P equal to 0. Okay, this indicating that. So P equal to 0, indicating at T greater than Tc, in these cases, G versus P plot. So P equal to 0 at this point, where A greater than, sorry, uh, A, B, C, both are greater than 0. Okay. And this is expressed in paraelectrics. This is called the paraelectrics. Where no polarization loss are there, you can see that with the increment of electric field, it's going at the same, it is following at the same line, that is paraelectric. Okay, this is paraelectric state. Okay. Now assume that if E not equal to 0, then del G del P equal to 0, what keeps? Here E involves. Okay. And if we ignore these two terms, then we get this. So E inverse equal to E by P. So A inverse equal to P by E. P by is nothing but chi. Okay, P by is nothing but chi. So this is nothing but chi susceptibility. Susceptibility. Okay. So this is the case for uh, sorry, this is the case for a greater than 0, which always tells about the paraelectric state or T greater than Tc. Okay. If we consider a less than 0, means at T less than Tc, when the temperature is less than this transition temperature, then what does it follow? What does it follow? Then the polarization versus energy, energy versus polarization, free energy versus polarization clock do not show one minimum. In these cases, there was one minimum. Okay, there was one minimum. Here you will see it was for T greater than Tc. Okay, but here for T less than Tc, you can see this minima point has been shifted to two minima points. At P, this is minus P remnant, this is plus P remnant, this point. Okay, and this is P equal to 0 point. So why this happened? Okay, uh, you have already we already seen about the P loop. Okay, it's not symmetric as well, so just look at the symmetry. For in these 2 points, what it shows that these types of two symmetry, so G versus P plot. Okay, G versus P plot. Okay, in these 2 points, and in this point, in first coordinate, what G versus P plot show? So G versus P plot show that there is a dip. Should be a dip in this. Okay, so this dip and this dip, there is a difference. This. Okay. So P minus Pr is less than plus P. Okay. So in this case, other should be changed there. In every uh, single coordinate, second coordinate, there should be value should be different. In this case, in here, here, and here is also the value should be different. Okay. At the fourth coordinate, value should be different. So depends on G and P. So at T greater than Tc means paraelectric state. Okay, in paraelectric state, for P equal to 0, what should be the value of G value? So G value should be this. Del G del P equal to 0. Okay, del G del P equal to 0. Okay, so we can move forward to that. Next question. Question number 3. That the Levi's law for a ferroelectric. So what is the main question is there that the Levi's law. Levi's law. You already know about the Levi's law. It tells about the susceptibility constant. And what is the relation between susceptibility and its dielectric constant? It's nothing but I plus 1. Means if you know the dielectric constant susceptibility value, you can also find out the dielectric constant value also. Okay. So this Levi's law is very important for a dielectric material, for ferroelectric cases. Okay, so susceptibility, how susceptibility varies with temperature. You have seen this famous relation of Levi's law, where susceptibility varies T by Tc minus 1. Okay, so this susceptibility varying with inversely proportional to Tc. Okay, so varying Okay, I was just checking the mic. Okay. Has gone there. Okay. Okay, now we can start. That Levi's law, we are just telling about the Levi's law. Okay. So it is inversely proportional to the, it is inversely proportional to the uh, TC. Okay. Where you can see that the ferroelectric material showing Levi's law. So N is a number of dipoles per unit volume. What N says? N is number of dipoles per unit volume of a material. Is alpha. N is that is a alpha. Alpha is dipolar polarizability, and Tc is defined as the ferroelectric transition temperature. If you see the variation of chi, you see that there is a certain jump at a particular temperature, that is T. Okay, so this is the transition of ferroelectric temperature. Okay, so it varies inversely proportional. Means with the temperature increment is varying at T greater than Tc. Okay. Ferroelectric behavior is observed below the Curie temperature Tc. Below Curie temperature, ferroelectric behavior observed, and where ferroelectric phase converts into a paraelectric phase at T greater than Tc. Paraelectric phases are observed there. And paraelectric phases has higher symmetry. Symmetry has higher symmetry than a ferroelectric phase. For example, the transformation of low symmetry tetragonal barium titanate. We have low symmetry, so barium titanate is a it has tetragonal symmetry at T less than Tc. Its Tc is approximately about 120 degrees centigrade. And for barium titanate greater than 100 Tc, 120, so T greater than 120, it shows cubic structure, which is, so cubic is more stable. Cubic is more stable. So this case of transition is also seen in a barium titanate. Okay, barium titanate is a pure perovskite material. Perovskite material, which has AbO3 structure. Similar type of material like lead titanate. Okay, it also show phase transition at around Curie temperature. Okay, where higher symmetric ephemeral to tetragonal like structures are also observed there. Okay, so these types of transition occurs due to the symmetry change. Symmetry and changes around Curie temperature. A paraelectric state is essentially a centrosymmetric higher symmetry state where dipoles are randomly oriented in a crystal, giving rise to zero polarization. Okay, so you can see that with the application of electric field, paraelectric phase, uh, this stable phase of ferroelectricity. Then after removing the phase, okay. So this is the for ferroelectricity below, and it's so below TC and above. So this is the paraelectric state. The Curie-Weiss law you already have learned in week 6, 7 lecture that the derivation. This is the derivation process. Derivation. What you have learned that for high polarization, mutual interaction of dipoles gives these types of arrangements of dipoles, which creates local field. This is not the actual field, not the actual field. This is not the actual field. This is very important. Local field and applied field are different from each other. Okay. So in these cases, Clausius-Mosotty relation, you already have learned that Clausius-Mosotty relation gives this local field relation, which depends on this polarization value. One second. So in the Clausius-Mosotty, on the basis of Clausius-Mosotty relation, we can also see that this local field is is greater than the actual field as it depends on the polarization. Okay, so thermal energy. Okay, so at T greater than T less than Tc. So you already know about this type of relation of polarization that it depends on epsilon minus epsilon s and epsilon naught p. and this is termed as a local field and n alpha. Okay, so E dash is not but E plus P by 3 epsilon naught and n alpha epsilon. Okay, and it's if we take it in this side, left side, and then try to find out the value of P only, then as n alpha by 3 epsilon tends to 1 value, as chi tends to 0, then 1 by chi tends to infinity. Infinity, then 0. Then this chi value and epsilon value are related to this constants. And this type of behavior, that is dielectric constant behavior and 1 by chi behavior, you can see 1 by chi is varying at discontinuously, varying continuously at t equal to tc. Okay, in these cases, at t equal to tc, the dipolar polarization, this is the dipolar polarization, all this you have learned in this lecture classes. So, I'm just recapping so that you can answer the question. Okay, so alpha D is much, much greater than, so alpha E plus alpha I plus alpha, that is electronic polarization, ionic polarization, and interfacial polarization. We do not consider this as at a TC. In these cases, only alpha D, only dipolar polarization exists. So what it varies, it transitions, there should be a transition from ferroelectric to paraelectric state. Here, 1 by chi varying linearly with 1 by linearly with at Tc, and then thereafter it is increasing, and dielectric constant varying in this fashion. Okay, dielectric constant is nothing but 1 plus chi. Okay, so we are just uh, in, uh, increasing this term, um, following this term and getting this value, that Tc value is nothing but this. So at T less than Tc, polarization is finite, that is dipolar alignment. At T greater than Tc, P is equal to 0, that is random dipoles. So these are the very two important points. Okay. At T less than Tc, there are polarizations value, P not equal to 0 value, and T greater than Tc gives the polarization value, no polarization value. And this gives you the paraelectric state. This gives you the ferroelectric state. Okay. So, this transition temperature, Curie temperature, is termed expressed in terms of n alpha and T and epsilon naught. So, Curie temperature versus T gives you n alpha by T. So, chi value turns out to be this, and from here, chi is varying inversely with Tc, and it gives chi epsilon relationship as this P by 3 epsilon naught. So, already you have learned uh, this much in your lecture classes. On the basis of this, you can now answer that Curie-Weiss law for a ferroelectric suggests that the susceptibility is inversely proportional to Tc. This will be a correct answer, and it is applicable in the paraelectric region only, as as we applied Kudiwai's law in T greater than Tc. Okay. Now we are moving to the question number 4. Okay. There were some technical problems in your mind. So just 1 minute. Just okay. So am I audible? Am I audible and visible? Am I audible and visible? Please tell in the message section. Message section, Anirudh. Okay. Okay. So there was a problem. There was a problem of internet connectivity, I see. Okay. So everything is fine now. Okay. So I apologize for this convenience. So we can now start. Okay. That question number 4. That is now we are moving to the second. Only two things. Everything about basics of ferroelectrics and phase transition and how free energy is varied with polarization at a specific temperature. Everything we learned about in the Clausius-Moffatt relation, Kurigai's law. Okay, now we are moving to the second order phase transition. Second order phase transition. We divided transitions order, first order, second order on the basis of temperature. Okay, on the basis of of temperature at T naught, at Tc, at T less than T naught, at T greater than T naught, at T greater than Tc, T less than Tc. On the basis of these temperature regions, at different temperature regions, the value of G, value of chi, value of polarization, how they varies, how they changes. Okay. On the basis of this, these types of phase transitions have been classified, second order, first order. Okay. So what first order type or what second order and first order type variation gives like mainly when we see polarization value, this is the polarization value. If we see the change of polarization value, okay, so polarization value, you see this type of second order phase transition. So polarization value is decreasing in this line. So decreasing at after up to 40 temperature, with temperature. Okay. So polarization value is decreasing up to 40 temperature. And for second order transition in this method, so there is a gradual change, not a abrupt change, gradual change. Okay. And for first order cases, this polarization value, this is the red colored polarization value, is decreasing abruptly. At this certain point, there is a bump. There is a bump. Okay. So this term is a abrupt change. Abrupt change. Abrupt change. Okay. Abrupt change of polarization gives this bump at a first order post transition. Accordingly, the changes of chi, this is susceptibility. Susceptibility, how it changes? It is also changes at Tc according to the Curie-Weiss law, inversely proportional. So how the 1 by chi value is changing? It is decreasing up to Tc and then increasing at the point of Tc. Tc is the transition temperature, Curie temperature. Okay. So in these cases, the second order phase transition, this term happens in a second order phase transition. How it happening? Okay, we will see later. For first order cases, there is also a bump. So in first order cases, it is not continuous. This is discontinuous. This is not continuous. 1 by chi is discontinuous. Okay, 1 by chi is discontinuous. And for first order. And for second order, this is the fourth order green colors. For second order, it is continuous. Okay, chi value is continuous. Okay. So these are some changes. These are some properties of a dielectric chi value and polarization value. So here you can see that how polarization values temperature T changing at T less than T. At T equal to T naught, it is changing this fashion. At T less than T naught, it is decreasing. Okay, with respect to T naught. So on the basis of this, how chi is varying and how polarization is varying in second order phase transition have been shown here. So this two follows this equation that you can see that at T equal to T naught, this is varying as to the power half. At T equal to T naught, is going to be 0. It depends on A naught B value. Similarly, it depends on 1 by A naught value and it is inversely proportional. Inversely proportional. Proportional. On the basis of these two relation, we can um, tell that how P and chi are varying, how P and chi are varying, how P and chi, these two terms are varying. But I have told for first order and second order cases. How first order and second order cases they are varying. Okay, okay, dependency is has joined. So now you can see that what will be the answer. So first that it shows the sudden change. No, there should not be a sudden change. There is a gradual change. So it shows the gradual change in the polarization. And next is susceptibility shows a gradual change at TC. Both properties, susceptibility and polarization, both shows a gradual change. Only gradual changes will be there. No abrupt change. What happens to a ferroelectric material when its temperature changes from T1 to T2? TC means when a ferroelectric material goes up to TC value from T1 to TC, how a polarization value, E value changes how, and epsilon R value, how both these changes. This is the question. Okay. So you have seen that uh, for this is case of second order case. Okay, second order. You can see that for second order there is a uh, gradual change for P, and for this is the abrupt change, and this is a continuous change. There is a bump for chi. So dielectric permittivity, that is the epsilon R value, how it changes up to Tc. This is the region. This is the region. Okay, this is the region where T less than Tc. So I am going from T1 temperature to Tc temperature, and in this region the dielectric constant is increasing up to Tc. So in this region, it's showing ferroelectric tetragonal phase, and in this region is showing paraelectric tetragonal phase. Sorry, cubic phase. That is cubic phase. That is tetragonal phase. That is more stable phase. Okay. So at up to Tc, dielectric constant is increasing, and polarization is decreasing. Polarization is decreasing. This is the question. What happens to the ferroelectric material when its temperature changes from a temperature T1 to Tc up to from temperature T1 to Tc, the polarization is decreasing, and from temperature T1 to Tc, the electric constant is increasing. So what will be the answer? Polarization value, sorry, it will be decreased value. Okay, so polarization value decreases up to Tc. This will be answer. And what will be the second answer? The electric constant value increases up to Tc. Okay, so B and C should not be correct. Okay. Question number 6. Barium titanate. This is also a ferroelectric material. Perovskite material, AbO3 structure. Okay. Where titanium, this is the octahedra. It shows two types of variation, tetragonal and cubic, for T less than Tc and T greater than Tc. Tc here is 120 degree centigrade. These are some basic information about barium titanate. So barium titanate is a ferroelectric material. So this is a ferroelectric. So it shows a dielectric constant value versus temperature plot. How does it give? It show up from at Tc. And polarization versus T value is decreased at a certain temperature, Tc. Okay. And it shows if polarization is second order transition, because polarization value is decreasing up to certain temperature, this is increasing up to. There is a no discontinuity. For polarization versus temperature, there is a no discontinuity. No discontinuity. Okay. So just see this figure that for barium titanate, whose transition temperature is 120 degrees centigrade. So when it we are increasing temperature from T2 to T1 to Tc to T3, means these are less than Curie temperature. So for Curie less than Curie temperature, it's going to be um, reduce of P, and when it is greater than Tc, it is P equal to 0. So P value always going to be reduced. You can see for T1, for T2, much polarization is given, and its polarization value, this PR value is going to be reduced with the increasing of temperature. So polarization value is going to be reduced at a particular temperature Tc, and for T greater than Tc, this type of behavior from this is a paraelectric behavior. Paraelectric behavior is shown in this figure. Okay. So what will be the temperature dependent plot? What will be the temperature dependent characteristics of ferroelectric material? There should be a phase transition from a non-centrosymmetric to centrosymmetric phase. Okay. Non-centrosymmetric, that is tetragonal. Centrosymmetric phase like cubic phase. Okay, this much amount of transition has also been occurred here. Okay. Okay, I'm just checking that whether it is connected properly or not. Okay. So if anyone face any problem, you can inform me. So phase transition from a tetragonal to cubic phase occurs, okay, in this direction. So this is the dielectric constant versus temperature plot. You can see at a transition temperature T from ferroelectric state to paraelectric states, transitions, and ferroelectric drops to 0. Polarization is 0 at Tc here. Sorry, in these cases drops to 0, and it becomes at Tc, it becomes paraelectric state. This so paraelectricity. So it is ferroelectric to paraelectric transition. Ferroelectric to paraelectric transition at least. Okay. So we can get the values of, this is the free energy value of how free energy value are changes. Free energy values are dependent on this is a function of polarization. Okay. And this is a function of polarization, and sigma also, this is a function of temperature also. We just consider uh, P and T, not sigma. Okay. So P and T values. So A, B, C, these are temperature dependent. These are temperature dependent. So please, these powers are taken for plus minus PS, saturation, polarization, two plus minus states. So even powers only have been considered because of the two states. One is plus, minus. So two states. So only even powers have been considered. Okay. So even power you can see 2 plus 2, 4 plus 6. So everything A, B, C are temperature dependent. So this G, how G is changing temperature. So E value is ultimately giving this value. So when A, B, C are positive, A, B, C are positive, then P equal to 0. Means it gives the polarization state, a paraelectric state for T greater than Tc. Okay. When A greater than 0. But for A less than 0, we take T less than Tc. Okay. This you already have learned that susceptibility is nothing but A inverse, which is nothing but T by E. On the basis of this, after putting this A value, means temperature dependent value, and ignoring these terms, we also get the G value as a function of T value up to T naught, T greater than T naught, and T much less than T naught is A less than 0. Means this portion and this portion. Okay, so free energy value is has a one minima for a ferroelectric, for a paraelectric state, for a paraelectric case, only one minima because of polarization is 0. And here, two minimas are there. Why? Because of plus minus PS state. Okay. So, two minimas are there for a P loop. There is a switching between PS plus PS minus PS or plus PR minus PR. Okay. So switching between ferroelectric state. This keeps switching between domain concept should be there. This much information gives plus minus PS value, which is responsible for minus PR and plus PR. This should be minus PR and this should be plus PR. This polarization state also giving to minima in the polarization value also. And in the case of second order phase transition, for T greater than T naught, there is a minima. In for T equal to 0, there is a minimum also, flat minimum, you can see. And for T greater T less than T naught, it shows ferroelectric state. That's two minima should be there. Okay. According to this relation. So P naught is varying with temperature with this, and so it decreases, and chi inverse 1 by chi shows this is 1 by 5. Okay. And the variation of second order transition looks like this type of behavior, polarization versus reciprocal of susceptibility. This is reciprocal. Okay, and This is the CV value. This is the specific capacitance value. Sorry, specific heat value. How specific it depends on CV. Okay, at constant volume. At constant volume. Okay. And how it depends on temperature is also given. It depends on A naught and 2B. And this is a diagram of barium titanate at different temperature. Just see the region of temperature. This is the region of one region of temperature. This is the one region of temperature. This is the another region of temperature. So in this region means minus 160 degree to 100 degree, minus 100 degree. You can see it shows a rhombohedral phase. Rhombohedral phase, due to which there is a rhombohedral phase to orthorhombic phase transition up to this temperature, 100 minus 100 degrees centigrade temperature. This is a rhombohedral to orthorhombic phase transition. Rhombohedral to orthorhombic phase transition occurs there, and there should be a bump there. Okay. And up to 5 degree, this is a 5 degree, up to 5 degrees centigrade. This shows orthorhombic phase. Orthorhombic phase is nothing but this, and rhombohedral phase is nothing but what? A not equal to B not equal to C. And at this temperature, tetragonal phases are there. Okay, tetragonal phases are there. Tetragonal phase. Here is also A not equal to B. Okay, but there is a difference of angle, and most stable figure are obtained at 120 degrees centigrade. So there are three phase transitions occur. Three phase transitions. Okay, barium titanate, three phase transitions. Rhombohedral to tetragonal at near about minus 100 degrees centigrade. Near about minus 100 degrees centigrade, and at orthorhombic to tetragonal at near about 5 degrees centigrade. Okay, and for tetragonal to simple QB occurs at near about 120 degrees centigrade. So these three phase transitions occur at different temperature, and their corresponding structural figures are also shown. And near about 150, 114, 1460 degree temperature, hexagonal figures are also can be obtained, but these mass temperatures are not getting in real, so we do not observe it in a real, not real case. So some scientists have also observed that. So we are mainly interested in these three regions. So everything tells us about the how phases are changes at different temperatures, at different temperature regions for a barium titanate material. Okay. So how dielectric constant is varying? How dielectric constant is varying? That this is nothing but how dielectric constant is varying. It's nothing but a temperature dependent. It's a temperature dependent property, and how it behaves at this phase, in this phase, in this region. You can see that in this region, tetragonal phase. Here is also ferroelectric material also. Ferroelectricity is observed there. Ferroelectricity is observed there. Ferroelectricity is observed there. That is P equal to not equal to 0. And after that, when above above 120 degrees centigrade, above 120 degrees centigrade, greater than PC, 120 degrees centigrade, it shows paraelectric state where P is equal to 0. So from this figure of P loop, this P loop transform into this figure of this type of transition. This type of transition, this should be symmetric. Okay, this should be symmetric means no polarization should be generated. Case of application of electric field. So this much transitions has been offered. This is termed as a tulip figure, and this is tetragonal figure. Okay, so these types of transition has been offered there. So on the basis of these concepts, you can now answer this question that a ferroelectric phase transitions is of second order. Although both options are given and a same, so so option A is correct, and option C is a that Tc of 120 degree centigrade is also there. Go to question number 7. That considering Gibbs free energy of a uniaxial ferroelectric material. Uniaxial ferroelectric material means ignore sigma stress value. Okay, so only Gibbs free energy is dependent on polarization and temperature. So only Gibbs free energy is dependent on polarization and temperature value. That's why it is given in this fashion. This is nothing but the Gibbs free energy expression. So here, when the field energy is minimum, we can get these types of behavior. So what is the behavior at T greater than Tc? What is the behavior at T greater than Tc? We already have learned that at T greater than Tc, it shows paraelectric behavior. Paraelectric behavior where P is equal to 0. A paraelectric behavior P is equal to 0. And when P is equal to 0, already have learned that it is dependent on P, it is dependent on sigma, it is dependent on T. Okay. So for inertial cases, G is only dependent on, we do not consider this. Okay, we consider only P and T. Okay, so for these cases, we have seen that this is a case of second order phase transition. You have seen that G value and P value are varying. There is a minimum value at T equal to Tc, where A is equal to 0. And for A greater than 0 at T equal to 0, there is also a minimum. Only one minima is there. Only one minima is there. One minima is there for G versus P plot. Only one minima is there, but at T less than Tc, it shows a ferroelectric behavior. Plus minus Ps consideration is also there. For this is for the case of these two minima. These two minima occurs at minus plus Pr and minus Pr occurs at these 2 points. Okay. So two minima occurs at T less than Tc where A less than 0. And in this case, A greater than 0. So value of A is varying. So when A, B, C, both are positive, 3 are positive, it is following this region, this value. Okay. And this is nothing but entropy. It is a temperature dependent. We are not interested in this. Second order phase transition is seen in Rosselli salt, case 204. Okay. So on the basis of this, we can now answer this P greater than Tc will be for A greater than 0, B greater than 0, C greater than 0. Okay. And for A less than 0, this is not correct. This actually tells about T less than Tc. Okay. And the material is in paraelectric state. Of course, the material is in paraelectric state. For A greater than 0, at T greater than 0, and this is not also correct, and these two are correct, and this also telling about the t less than tc value. Okay, and this is for t greater than tc, t greater than tc value. Okay. Question number 8. Consider the equation in the question number 7 that ap plus dp to the power 6 uh, c to the power 4 ap square to the power 4 6 minus c equal to 0. This was given in question number 6. What will be the value of a? It has already been told that when the value of a greater than 0, it is lying at t greater than tc. And when the value of a less than 0, it is lying at t less than tc. It denotes about ferroelectric phase. It denotes about paraelectric phase. Okay, the similar figure. This denotes about paraelectric phase plus here uh, minus here to be there. So there is an energy graph. Okay, there is an energy graph. And this is nothing but polarization value. How polarization value is decreasing with temperature. Okay, so polarization value is decreasing also at temperature. Polarization value is decreasing up to transition temperature. Okay, so all these are the second order phase transition. Okay, so this is the question is also based on the second order phase transition. What will be the value of A and B? So value of A in this case, value of A will be less than 0 for t less than tc. For t less than tc, value of B will be A will be A naught, but B value should be greater than 0. B value should be greater than 0 and others are incorrect. Okay, so only two options are correct. Question number 9. Just see this figure. Just see this figure. And uh, and just see this figure and try to find out the answer. In this following plot, I'm just checking everything is fine or not. Okay, three curves are given. This green blue curve, what this signifies, this curve 2, what this signifies, and what curve 3 signifies. So curve one is nothing but the polarization curve. This is a Curie temperature polarization curve, which polarization is decreases up to p value is not equal to 0 up to t equal to tc. Okay, p value is 0 at t greater than equal to tc. So this is a polarization curve, and curve 2 is the dielectric curve, epsilon r, dielectric constant curve. Dielectric constant, there is a certain peak at tc. Uh, at tc, there should be certain values. At tc, maximum value of dielectric curve has been observed at tc. Okay, and this green curve is nothing but the 1 by chi value, 1 by chi value, the inverse of susceptibility. So nothing, there should be the option of 1. 1 is telling about the polarization, second is telling about the dielectric constant, third is telling about the inverse susceptibility, which is 1 by chi. in a second order phase transition only. This plot is correct only for second order phase transition. For first order phase transition, there should be a jump at this point. There should be a discontinuity in chi also, and there should be dielectric constant variation should be this. Okay, there should be a discontinuity in first order, but this is case of a second order. Okay, so this is the case of a second order case. You can see also. Okay, you already have learned about this, how uh, ferroelectric and paraelectric phases are converted. And for second order phase transition, polarization is continuous, no latent heat is generated, and the discontinuity in the second derivative. So del 2g, del T2, this is discontinuous. Discontinuous, okay. And how chi is, you already have learned about this. So how chi is varied with how chi 1 by chi is varied with temperature. Temperature you already have. So these are all have explained in your lecture class. Okay, how it dependent on A and B. You can see how 1 by chi is dependent for T greater than Tc, and for T less than Tc, this how chi A is dependent on temperature, and how chi B is temperature dependent for T greater than Tc and T less than Tc. You can after uh, this, on the basis of these two, 1 by chi is varied at temperature Tc, like this. Okay, this is the variation. On the basis of this two, this is phi b. It has two slope, and this has one slope value. Okay. So on the basis of this, you can just answer this question number 2 should be the answer of this question. Okay, now we are moving forward to the question number 10. Okay, at Tc. Okay, now the question is based on this first order phase transition. First order phase transition. First order phase transition. So you must have to know about how the first order phase transition occurs. In case of second order phase transition, the question is telling about at T equal to Tc. Okay. In case of second order phase transition, we seen that T temperature range T, Tc, and T greater than Tc. T less than Tc, T equal to Tc, and T greater than Tc. First order, we consider a temperature T naught. Okay, T naught. Where T naught is like from three regions we consider T less than T naught, T greater than T naught, T naught is less than Tc, or here is also you can consider T naught equal to Tc, or Tc is T greater than Tc. T greater than, sorry, this should not be T greater than. Okay. T greater than Tc should be there. Okay. You can see this figure that this is the first order phase transition. This is the first order phase transition. It is showing about at when A greater than 0 means T greater than Tc. In this region, only one minima is there at T greater than Tc. This is nothing. This is just like a paraelectric region, paraelectric case. Okay. So A less than 0 for B less than 0. B less than 0 is very, very important. For B greater than 0, only second order phase transition occurs. But for B less than 0, only the first order phase transition occurs. This is the basic difference. For A less than 0, we consider only the T less than Tc. Okay. So now when we are moving to the T less than Tc region, it also considers T naught region. So at T equal to Tc, A equal to 0, this gives the ferroelectric behavior means two minima should be there. There is a one minima, sorry, at T equal to 0, and there is a two minima. Okay, two minima is there, but at the intermediate point, T less than Tc. Okay, sorry, this is the T less than Tc less than T, the A less than 0. This gives two minima. This figure gives two minima. Okay, but what will be the at the minimum in between them? These two figures are seen between them. There are three minimas are there. One, two, three. Three minimas are there. So three minimas. Okay, three minimas are there. So this is the typical feature of the first order phase transition. First order phase transition. This is the typical feature of first order phase transition, that three minima would be there. Okay. So in between them, so in between Tc, when A less than 0 and B also less than 0, gives you three minima position. This behavior is a new behavior. Okay, new behavior from um, uh, which is new behavior shifted from second order transition. Okay, so on the basis of this, we can now answer that there is a three minima, at different p values, indicating on at p equal to 0 after equal to 0 p. So three minima are there, or there is no one minima, two minima should not be there, one minima is there. So only three minima is correct answer for this. Now question number 11. During polarization switching of a ferroelectric material. So for polarization switching mainly determines the domain structure. Due to domain structure, occurs due to domain structure variation. Domain structure variation. This domain structure variation of ferroelectric material. So how G ferroelectric versus polarization plot? This varies for a typical ferroelectric behavior, and this varies for T less than Tc for a ferroelectric material. Okay, these are the differences. This is for para, for ferro. There are two minima, one. But how they are occurred? How they are occurring there? This is the question, that in which region? This is due to PS value. But which region? This is the question is mainly for fourth quadrant of a PLO. Okay, means in this region, in this fourth quadrant, in this region. Okay, how this G value is varying. Okay, now see this figure, that G versus polarization plot. Okay, gives a minima for T greater than Tc, and gives two for T less than Tc at minus PR point, at plus PR point. And this is a central position. So you can see that polarization switching mainly occurring at this point, point B and point E, where so you can see that this region, this is linearly varying with the electric field polarization, and this is non-linear variation. Non-linear variation, and this position it is stabilizes. Okay, okay, and this after the switching of electric field, after the reversing of the electric field, at this point, only this is the saturation PS point, this is PR point. So at this PR point, every polarization going to the zero after the application of zero field. After the application of zero field, there still polarization exists. So this polarization, if you want to reverse this polarization region at this region, so how? At this polarization region, 2 plus PR, only plus PR varies. So there are two minimas exist at these 2 points, at this E point and B point. So B and E point is two minima points. So these 2 points have been given it there. But for second coordinate, so for first coordinate, we are moving this PR value plus PR value to the minus PR value. So this line is moving to the B point. So there is a higher dip at this. These two dips are similar at this point because of PS value. Okay, remnant polarizations are there. There are highest polarization, PS value, highest polarization. Similarly, this figure, there at this point, third coordinate PS, there should be a minus PS. This is due to the minus PS. And at this point, this is due to the minus PR value and plus PR value. But for what will be this figure? The question is this. What will be there? There should be, in this region, should be PS, how PS? Plus PS is greater than minus PR. Also minus PS. Okay, this is greater than minus PS. So, in this region, that G for plus PS, G for plus PS is less than G for, G for plus PS is less than G for minus PS. So this should be correct. Sorry, this should not be there. G for this should be correct. That PS minus PS is plus PS is greater than minus PS, because in the fourth quadrant, this is the fourth quadrant. This is the fourth quadrant. This is the fourth quadrant. Okay. Here plus PS is greater than minus PS. Okay. So G value should be greater, because higher dip of plus PS has higher dip. Plus PS has higher dip. Okay. So this is the theory portion, the conceptual part for question number 11. Now we are moving to the question number 12. This is also in a first order phase transition. Okay. So continuity and discontinuity phases of the first order phase transition, that you have seen for this figure that the first order phase transition, there is a 3 minima position. Okay, 3, 1, 2, 3, 1, 2, 3 minima position at t less than t naught. And this is discontinuous position. Discontinuity in P, discontinuity in 1 by chi. 1 by chi is also discontinuous. Okay. And this the sudden drop of polarization, there are t less than t greater than tc, where A is positive, t equal to tc, where A is 0, t less than t naught. So 3 regions are there, but here always b less than 0. Okay. So most important features is there that LS transition, liquid solid transition, liquid solid transition. So discontinuity 1 by chi is also observed there. Okay, this is I have explained. So here main important thing is the for first order case 1 by g, second order case 1 del to g is so this is discontinuous in first order case. Latent heat is generated due to liquid solid transition. Okay. First order case is observed in barium titanate and perovskite structures. Second order is observed at Rochelli salt and lithium neobaton. Okay. So on the basis of this, you can now answer that first order phase transition susceptibility is not continuous. So this is incorrect. So this is correct that discontinuity in the susceptibility across the transition temperature you have seen it, and discontinuity in the first order derivation of the free energy. Okay, so these two options are correct. Option B. Option C is incorrect due to this is for second order. Okay, this is for mainly second order cases. Question number 13, that first order transition shows, this is same that first order transition, how first order transition. However, evaluation of latent heat, when this is 1 by chi, how it discontinuity is there, and there is a liquid solid transition. Latent heat is nothing but the heat required for phase transition. Just like liquid solid. Okay, liquid solid transition at a particular temperature, just like 4 degrees centigrade at a 0 degree centigrade water, sorry, for 0 degree centigrade water and ice. Okay. So this is in liquid solid phase transition, latent heat is generated and del G del T is discontinuous in the case of first order transition. Okay. Based on this information, you can also answer this question, that evaluation of latent heat at a particular temperature Tc, and discontinuity in polarization is Tc is also there, and these two are not correct. So only two options are correct. Continuity in entropy is nothing but del G del T at constant T. So del G del T constant T, it is also not correct. Okay, because for G value is not continuous. It is varying. Okay, varies. Three different meanings. So in these cases, the three meanings should be there. So S is not continuous. Okay. Question number 14. For the first order transition, this also in first order transition question. For the first order transition, that the slope. Okay, the question is about slope of the plot between 1 by chi inverse versus A. Okay. So you everything learned about this, okay. You have A changes here, B always less than greater than 0. So there is a discontinuity in 1 by chi at a transition temperature. Okay, discontinuity should be there. Discontinuous or the continuity is there. So discontinuity is there. Del G del T is nothing but the entropy. It is discontinuous. Okay, first order phase transition in case of first order phase transition. So on the basis of this relation, polarization discontinuous, entropy discontinuous, this is first order phase transition, gives you latent heat, and this expression gives continuous value of solid latent heat 0, but for second order generation. Okay. After applying E equal to 0 and this condition at equilibrium condition, after applying this, we can get the value of P this, and after putting this value for P less than 0, okay, this is discontinuous value, we are getting 4. So mainly 1 by chi B is equal to 4A for T less than Tc in this region. Okay, so what is the slope? This is the slope. Y equal to mx. Slope is m. The slope is nothing but 4. The slope value is determined. On the basis of this, first order phase transition, second order phase transition, how they are varying. G is continuous, discontinuous, G is continuous, this is discontinuous, yeah, this is discontinuous, this is continuous, this is discontinuous. Yeah. Okay. So here G value, S value, and C value have been shown here. How they are continuous and how they are varying with temperature has been shown. Okay. So you can now answer that. This will be 4. So this is the correct answer. So last question, question number 15. The area under the curve of a PE loop, area under the curve of a PE loop hysteresis loop, what does it signify? Okay, so when a PE loop is generated with the application of electric field P, how P is changing, it is P. This is the typical figure where this red portion is telling about the energy loss density and this green portion is telling about the stored energy density. Okay, upper part. So just so this is the area between P and E when this is going and this is reversing back. This is also called a W recoverable energy density. Okay. Recoverable energy density. This is the energy loss. Okay. So this is the stored energy. This is the lost energy. This only coordinate. First quadrant. First quadrant. We only find it in a first quadrant. Okay. We only measure in a first quadrant. So what will be the area under the curve PE loop of a ferroelectric is manifested as a energy dissipated in a dielectric switching. Okay. So here the switching, in this case, dielectric switching PR value. Okay, here dielectric switching occurs. So at this point, dielectric switching, this tells us about the energy dissipation in dielectric switching. Others are not correct. Energy required, no, it is not energy required difference. The total charge density, no, it is also not. So only the dielectric dissipated is area under the curve P loop source. Okay. So I have tried to answer all the questions in this section. Okay. So you can now I have taken that I am just seeing that all the questions have answered properly or not. So question number 13 is done, 12 has done. I have done 11 also. I have done 10 also. I have done 9 also. Okay. 7 also. 6 has been completed. Okay. 5 has also been completed. Question number 4 has also been completed. Number 3 has also been completed. Question number 2 has also been completed. Question number 1 has also been completed. Question number, okay. So every question I have answered, every questions. Okay. So is there any question? Uh, is there any question you can ask me? Is there any question? Okay, so that's it for week 7 assignment problem. Only one assignment problem is left for the next week. After that, it will be finished. And okay, so next you in the next week on Tuesday at 6 p.m. Okay, so we can now leave this meeting and let's see on the next week. Okay, thank you. We can now leave this meeting.